In this video, we'll be doing a theorem which is to justify the RSA setup. So here is the RSA setup that I've discussed in my last video. And in the encryption process, we see that there are two integers n and e which is made public by LIS, and there are some information which is kept secret. So let's start from this RSA setup. LIS chooses two large prime P and Q, take their product which is n, and they calculate phi n, which is P minus 1 into Q minus 1. Phi n is Euler's Totten function. LIS chooses E such that the GCD of E and phi n is equal to 1 and calculate D, which is the multiplicative inverse of E. Now these two are kept as public information, and then D, P, Q are kept as secret information. Bob wants to send a message M, so it looks at N and E. Because E is public, so M raised to power E is calculated and Bob sent C to LIS. Now once LIS receives C, LIS compute back the message M as C to the power D mod N. Now here if we notice, what is the point? When Bob computes C, so Bob computed C which is congruent to M to the power E mod N, whereas the original message was M. And when LIS computed the original message M which is congruent to C to the power D mod N. So we want to understand how these two congruences help to deduce the same original text, and corresponding to this we have this theorem as. So in this theorem we say that we have the same setup. Let n is equal to pq. This is the product of two distinct prime, and there are two positive integers d and e, such that they are related as d is congruent to 1 mod phi n. Then for all integers m and n, m raised to power ed, this is congruent to m mod n. So therefore, if c is congruent to m to the power e mod n, then we have m is congruent to c raised to power d mod n. So this is the same setup. If c is congruent to m to the power e, therefore m is congruent to c to the power d. So this justifies to our this step, and in the same way we can work with the RSA process. Now let's look at the proof of this case. Let's first look at this one. If I know that the star congruence is satisfied, then this will hold. We know, I'm just assuming at this stage, m to the power ed is congruent to m mod n. So here we are just assuming that this star holds, assuming star hold. In this case, if c is congruent to m to the power e mod n, so what we can do is, here we can raise both side the power d. So raising on both side to the power d, we will have m to the power e raised to power d mod n, and which is same as m e d. We assume that this 1 is true. Now m to the power ed is congruent to m from 1 mod n. So we get c to the power d is congruent to m. This proves the second congruence. If I assume the first congruence hold, then the second congruence is also hold. This establishes the fact that if we can prove that m raised to power ed is congruent to m mod n with these given conditions, then the other congruences obviously hold. Somebody select a message in this format that can be deciphered. Now let's see what is the proof corresponding to the star equation. For the star, or we'll say to prove star, let's see what we have the setup. We have n which is the product of two primes, and we have the phi n which is equal to p minus 1 into q minus 1. E is selected in a way such that its GCD with phi n is equal to 1, and then we have selected ed which is congruent to 1 mod phi n, or we can say this is congruent to 1 mod p minus 1 into q minus 1. Now here I am going to recall the Euler's theorem. This is the generalization of the Fermat's theorem. Euler's theorem said that if you choose an integer a, so let us a is any integer, and another integer we select n, such that the GCD of a and n, this is equal to 1. Then a raised to power phi n, this is congruent to 1 mod n. We have proved this in my other video. So now using the Euler's theorem, we want to prove this, that m raised to power ed, this is congruent to m mod n. This we want to prove. So there is no restriction on this particular m. This GCD with n can be 1 or it may not be 1. So let's put up some restriction. So the first case we will consider here is that GCD of m and n, this is equal to 1. And as we know that ED, this is congruent to 1 mod phi d. So we can write ED, this is equal to 1 plus k times phi n. So it's a multiple of k is an integer. This is equal to 1 plus k times p minus 1 into q minus 1. And here, because I have considered that the GCD of m and n is equal to 1, so you can apply Euler's theorem, which I have just stated. So by Euler's theorem, we can write m raised to power phi n. This is congruent to 1 mod n. And now we have in the exponent, we have phi n, and we already have an exponent formula for phi n value is here. So I'm going to replace this value. So we can say m raised to power ed, because this is what we require here. This is congruent to m. Ed should be replaced by 1 plus k times phi n. So this is 1 plus k times phi n, which is congruent to m into m to the power phi n and then whole raised to power k, which is further congruent to m into m to the power phi n. We have just shown that this is 1. We can see that it's here. We have shown using the Euler's equation, this is congruent to 1 mod n. So I can replace this 1 raised to power k, which is further congruent to m mod n. So our first case is proved that m to the power ed is congruent to m mod n. In this case, I have considered that the message which is m, its GCD with n is equal to 1. And here, of course, this message has a numerical digits. So this is an integer. This integer GCD with n is equal to 1. Now let's take the other possible cases. Now we'll take the other possible cases. In this possible cases, the GCD of m and n can be greater than 1. And as we know that n is equal to pq. So to calculate G, and both of p and q are prime. So we'll see p and q, these are prime. The possibility of divisors of n. So what are the possibility of divisor of n? Either the divisor of n is 1, or it can be p, or it can be q, or it can be n itself, which is in that case pq. If n is equal to 1 and m may be anything, m is any integer, then the GCD of m and n, this is 1, because in this case, if I just take n is equal to 1, their GCD cannot be larger than 1. So this brings back to our previous case. Or the other possibility is if n is equal to p. In this case, it is possible that the GCD of m and n is equal to p. Let's take this possibility. So here, let GCD of m and n, this is equal to p. So if this is equal to p, because they have GCD, so m is also congruent to 0 mod p, and we can say that n is also divisible by p. So here we'll say that p divides m, and so we can say m to the power ed, this is congruent to 0 to the power ed, this is congruent to 0, which is congruent to m mod p. Because p divides m, so p divides any exponent corresponding to m. So this congruence will trivially hold. In this case, we have also assumed that obviously that the GCD is p. So here we have assumed that q does not divide m, which means the GCD of m and q is equal to 1. So we can apply Fermat's theorem or the Euler's theorem. Fermat's theorem becomes the particular case of the Euler's theorem, because in this case it is prime. So we'll say m to the power q minus 1, this is congruent to 1 mod q. So we again want to verify what is m to the power ed. This is congruent to m 1 plus k times p minus 1 into q minus 1. This is congruent to m to the power q minus 1 raised to power k p minus 1. And this is congruent to, because this is congruent to 1. So this is 1 raised to power k times p minus 1. Similar math will follow up, which we just have done. We will see that even in this case, m raised to power ed is congruent to m with respect to mod q. Earlier we have shown this with respect to mod p. So here we said that p divides m, maybe q does not divide m. So from both of these, we can say that p divide m to the power ed minus m and q divide m to the power ed minus m. P and q are prime. So as the GCD of p and q is equal to 1, So P and Q product will also divide this thing, which means m to the power ed, this is congruent to m mod pq. So we get this result. And in the other possibility, so other subcase could be that P does not divide M and Q divides M. So similar to above calculations, we find M to the power ed, this is congruent to M mod PQ. So this will hold. Now the third possibility is that both of them divide. So when the both of them divide, so that becomes let's say case 3. So in this case, P divide M and Q also divide M, or we may say that the GCD of M and N, this is equal to PQ. So in this case again, M raised to power ed, this is congruent to 0 raised to power ed, because M is fully divisible by P and Q both. This is congruent to 0, which is congruent to M mod N. So in this case, this is straightforward. This is just a trivial congruence, because if P and Q divides M, then their product PQ will also divide M, or I can say N divides M. So when N divides M, so M is congruent to 0, and you can have any power which is divisible by N. So this congruence which we wanted to prove M to the power ed, this is congruent to M mod N. We have proved that whatever this message may be, its GCD with N may be 1 or greater than 1. We will prove. The only criteria is that N should have the product of 2 prime, so that it has fixed option. In this case, once this congruence is hold, we have seen that whenever if C is congruent to M to the power E mod N, if we have a setup of this type, then M is congruent to C to the power D mod N will also hold, and hence the RSA setup works. So let's take an example further to just verify this RSA system and just to apply the system. Suppose that an RSA public key is N is equal to 55 and E is equal to 27. So in the practicality, difficulty is because whenever we have been made the two integers public, that is N and E, it is hard to factor an integer which consists of hundreds of digits. So this is a problem. How we can factor an integer or the factorization into two large primes P and Q, which is the product that will give us N. But in this question, because we just want to see how the system works, we may consider that N is equal to 55 and this is the product of 5 into 11. So 5 is one prime and 11 is the another prime. Now we notice that Alias has this information public, that is N and E. N is given as 55 and we know what are the prime, P and Q. P is 5, let's say Q is 11, and we have access to E, that is 27. I need to know the private information with Alias, so this was the public information. In the private information, we need to know what is D, P, Q. P and Q we have just identified. P is 5, Q is 11. And I also need to know what is D. D in the system was E into D, that is congruent to 1 mod phi n. So we will have to calculate what is phi n. Phi n is 1 mod P minus 1 into Q minus 1. This is congruent to 1 into mod P, we have calculated 5, so that is 4 into 10, that is 40. So I need to know E, we already know that is 27, 27 into D. Now if you look at this problem, this is like a linear congruence. I need to solve a linear congruence, or I can solve this as an extended Euclidean algorithm. To write this into extended Euclidean algorithm, so we need to find what is 27D plus 40 times K equal to 1. So this looks like a linear Diophantine equation or linear congruence. So we will applying extended Euclidean algorithm. We will find what is D and K, and so we find that D is equal to 3. Once we have identified D, we know how the Bob has applied. Bob knows the original message M and Bob must have calculated C, which is congruent to m to the power e. E was public with respect to mod n. So this is the ciphertext which is given to us in the problem. The ciphertext is C equal to 4, but we do not know what is the original message. So for this deciphering process, Elias need to calculate m, which is congruent to ciphertext raised to power d mod n. Now since Elias have an access to d and to the ciphertext, so we'll calculate m, which is congruent to c to the power d. That is congruent. C is 4, D is 3, and so this is congruent to 64, which is congruent to 9 with respect to mod 55. So this is always with respect to mod n. So that means the original plain text is 9. And in case we want to identify the letter correspondingly, so we can identify the original letter, that is I. And here when I claim that this letter is I, here I have used A as 01, B is equal to 02, and so on, Z equal to 26. In case we have used this A as 00, B as 01, and we use Z equal to 25, in that case my original letter could be G. So this way we can apply the RSA system.